Welcome to the massive open online course on Aspen Plus. Today's lecture is a part of a lecture series to be taught in week 3. We will learn the basic process modeling part, which will contain the simulation environment, setting streams and input data, adding the input operations, namely heater, flash drum, valve, distillation columns, to be very precise, rat frac and distill, compressor, pump, and combustion chamber. The combustion chamber will be essentially a stoichiometric reactor. Now, all of these unit operations which I have mentioned right now, which are written over there on the slide, they already have been discussed. They have already been discussed in our previous few lectures, but today we will learn them in detail. We will see how these unit operations can be set up in a plant-wide structure, how they are called from the menu, how they are interconnected, and how the simulation is run on the entire plant-wide process, what would be the expected results, whether it matches with the physical conditions, and then we shall analyze the result. And at the end, we shall talk about some specific case studies, which will be necessarily some kind of sensitivity analysis. And this sensitivity analysis will be based on the change in input variables to these processes, which we'll discuss right now. First, we will talk about the problem statement. Now, we will take the example of an hydrocarbon treatment process. Now, this hydrocarbon treatment process is a very common thing in petro industries. In hydrocarbon treatment, we treat hydrocarbon gas, which is essentially the mixture of various hydrocarbon gases, and then we separate them and we get useful products out of it. The problem statement is something like this. Aromatic rich hydrocarbon gas whose flow rate is 100 kilomole per hour, and it is at 10 bar pressure and 15 degrees centigrade temperature. They have this following composition. So we have 15% methane, 15.5% ethane, 7.5% propane, 11% N-butane, 12% cyclohexane, 20% benzene, and 19% toluene. It should be treated to recover most of the hydrocarbon as useful products. What are the products? LPG and benzene and toluene aromatics. So these are the products that we are expecting out of the treatment. So this hydrocarbon gas is initially passed through a heater operating at 40 degrees centigrade and 10 bar. Now you see, heater is needed to increase the temperature from 15 to 40 degrees centigrade. So if we have a heater, we will have the gas entering here at 15 degrees centigrade, and it is expected to come out at 40 degrees centigrade because the heater temperature is 40 degrees centigrade. And it does not encounter any pressure drop across the heater because this heater is operating at 10 bar and the hydrocarbon gas is also at 10 bar. So there is no pressure drop across it. So Now this warm feed, because it has already passed through the heater, so now it is warm. The warm feed is flashed in a column. So there will be a column somewhere after the heater. So this is the heater output. So this will be flashed in this column operating at 40 degrees centigrade and 10 bar in series with a pressure reducing valve. So if the temperature is constant, then until and unless the pressure is released, it will not liquefy. Okay, there is no point in flashing them, because flash means there will be separation of vapor and liquid. Now for the liquefaction to happen, we have to reduce the valve. We have to reduce the pressure through a valve. Now here it is 10 bar pressure, here it will be 2 bar, because pressure drops to 2 bar across the valve. Okay. Now one more information is there, that flash tank operates adiabatically. That means the heat loss or heat gain is equal to 0 across this column or flash tank. Now the liquid has gone below, the vapor has gone above, so this vapor is called the leftover gas. So the leftover gas will flow through the top of the flash tank and it will be burnt in a combustion chamber. So there will be a combustion chamber here. So this is the combustion chamber, and to burn this leftover gas, we have to supply air, because without air the gas cannot be burned. So the combustion chamber is operated with 100% combustion. So there will be no gas, that whatever is there, methane or ethane or whatever, there will be no trace of methane or ethane at the outlet. Outlet will be completely carbon dioxide and water. So air will come with composition 79% nitrogen and 21% oxygen, and it will have flow rate 1200 kilomoles per hour, and here it will have the pressure 10 bar and 50 degrees centigrade. So this is the operating condition of air. Now it will form carbon dioxide and water, as I said already, and there is no pressure loss across the combustion chamber, which operates adiabatically. So there are two information hidden here: no pressure loss and operates adiabatically. Now here we find the combustion chamber. The combustion chamber is governed by the following reaction stoichiometry. So these are the reaction stoichiometry. Methane is burnt with oxygen to form carbon dioxide and water. So is ethane, propane, butane, cyclohexane, benzene and toluene. All of them are burnt with oxygen to form carbon dioxide and water. They have their own stoichiometric proportions, but they all form carbon dioxide and water. And mind that it is 100% combustion. Now we come to the bottom of the flash tank. So top of the flash tank is leftover gas which went to the combustion chamber. Bottom of the flash tank, after it was passed through the valve where the pressure reduces and liquefied, here it is said the liquefied stream is fed between 7th and 8th tray of 15 tray equilibrium separation column. So essentially there will be a distillation column where the stream is fed between 7th and 8th tray of a total 15 tray column. The column has a partial condenser at the top. Partial condenser means there will be vapor and liquid both in the condenser, and there will be negligible pressure drop across the column, and the partial condenser operates at 1.95 bar. The reflux ratio is set at 5. That means if 1 mole of vapor is going out of the partial condenser, then 5 mole will come back to the column. So reflux ratio is set at 5. While 20% of original hydrocarbon feed is expected to be recovered as the vapor distillate. So here it is 20% of the original vapor. So what was original? Original was 100 kilomole per hour, if you remember, just a few slides back, if you remember. It was 100 kilomole per hour. 20% of that will be recovered as the vapor distillate, which is essentially LPG. Now this distillate will be compressed to 5 bar. Here it was operating at 1.95 bar, so it will be compressed to 5 bar using an isentropic compressor with 88% efficiency. So this is the vapor distillate at 1.95 bar. Here it will be 5 bar LPG, which will be recovered after the isentropic compressor. Now the bottom stream of this column is sent for further distillation. So bottom stream will essentially have C6 and C7, mostly benzene and toluene. So all the heavier keys will come at the bottom. So this bottom stream will be sent for further distillation. So this is the bottom stream, and there will be a further distillation column. Here the second column will have 20 trays, and the feed will be given at 10th tray. This column uses a total condenser. This is a total condenser. That means there will be no vapor distillate, only liquid distillate. This condenser operates at 1.9 bar, and the reboiler at the bottom, it operates at 2.1 bar. 60% of the column feed is recovered at distillate. So it is 60% of the feed. That means D to F ratio is 0.6. Now essentially this is rich in C6 aromatic. So this is C6 aromatic. The reflux ratio is 4. That means if 1 mole of distillate is coming over here, 4 moles are sent back to the column. The bottom stream of the second column is rich in C7 aromatic, which is pumped with 66.7% efficiency and a pressure increase of 0.5 bar. So there will be here, there will be a pump. So here it is 2.1 bar, and here it will be delta P of 0.5 bar because of pumping, and the pump operates at 66.7% efficiency. Now here we have the complete process flow sheet in front of us. We can see all the unit operations that we have discussed, namely the heater, flash tank, combustion chamber, column 1, column 2, isentropic compressor and pump. The feed hydrocarbon is entering in the heater, whereas air is entering in the combustion chamber. So the heated hydrocarbon is flashed, where the major components are flashed and liquefied. The leftover gas is being burnt in the combustion chamber. The first column, it separates mainly the LPG and the C6, C7 components. The LPG is being formed by passing the vapor distillate from column 1 through the isentropic compressor, while the bottom product of the column 1, which are essentially C6 and C7 products, they are again passed through the column 2, and these are the condensers. These two are condensers. You can notice that this is the partial condenser, so vapor distillate is coming over here, whereas it is total condenser, so it is liquid distillate. So it is liquid C6 product. And here you find the C7 product over here, which is coming out through pump. Now here all the specifications are written. So while developing the Aspen Plus model in the simulation environment or the property model, you have to define all these specifications. You have to remember them, or you can take a printout of this flowsheet chart and then take the you can form the model in the simulation environment. Now, what are the tasks that we have to do? First, obviously, we have to develop a steady state model of the plant using Aspen Plus. Then we have to verify material and energy balances of the unit operations and unit processes. We have to check the composition of the process streams. The inlet composition definitely we have to set, but the outlet composition, which will be the result of the process analysis, the process running of the process, that we have to check. Then analyze the process conditions such as temperature, pressure and flow rates, and perform a few case studies on the changes in the following process conditions. So this we have identified for this case study. One is decrease the heater temperature and see what happens. Change the discharge pressure of the valve, because The discharge pressure of the valve decides how much liquefaction will happen, okay, after the valve, after the flash tank. And finally, we will change the reflux ratio in the distillation column and see what would be the results of change in reflux ratio. Basically, the distillate condition will depend upon the reflux ratio, that is the purity of the distillate. Okay, so we will see all of them. Now let us go to the simulation environment now. So the Aspen Plus is opening. We have to give it some time. Okay, so the Aspen Plus has been opened. Now we have to open a new flow sheet. So it is a blank simulation, and we'll run create. Okay, so first we have to add in the components. What are the components do we have? Let us see. So we have these components: methane, ethane, propane, N-butane, cyclohexane, benzene, and toluene. So we have to add in these components one by one. Let us write methane. Now these are the conventional chemicals. So if you write methane, it will understand you are looking for CH4. So methane it will understand, ethane it will understand, propane also it will understand, N-butane, very common, but cyclohexane it may not, because see, it has a very limited only 7 letters are available for defining your component ID. So cyclohexane it may not understand what it is. If you write cyclohex, it may not understand. So it is writing conventional, okay, but it doesn't identify anything like the ones which we have already defined. So what we can do is we can say find. So here we'll write cyclohexane as full, and we'll say find now. So it will search. Yes, now it has searched so many items which are similar to the term cyclohexane that we have written. Okay, now this is the one which we are looking for, C6H12. So we will say add selected compound. Once we do it, then you can see it has added. cyclohex, which couldn't find the component name, it has added. Okay. The other two are very simple, benzene and toluene. So we write it in this fashion, it will accept. Okay. Now we have to press next, and we have to see what are the property methods that we can use. Now we have a method assistant. We can take the help of method assistant. If you know what method you should use, you can directly look for it. Otherwise, you can take the help of method assistant. So this is the method assistant, property method selection assistant. You have to specify component type. It's a hydrocarbon system. Does the mixture contain petroleum assay or pseudo component? Yes, it has. In the system is vacuum condition? No. So you can use these methods. Use Chow-Cedar or Grayson if the system contains hydrogen. But our system doesn't contain hydrogen, so you can use Brown-Ketten or an equation of state method such as Swayam and Peng-Robinson. Now let us choose Peng-Robinson method. So base method is Peng-Robinson, and here you can modify. You can modify the equation of state method, liquid molar enthalpy, molar volume, etc., heat of mixing if you have. So you can modify your Peng-Robinson method based on some extra data that you may have. We don't have any such data, so we can just go forward with next. Then it will quickly calculate the binary interaction, temperature dependent binary interaction, methane with ethane, methane with propane, methane with N-butane, ethane with propane, ethane with N-butane, propane with N-butane, and so on. Okay, so all these temperature dependent binary parameters will be calculated for you. Now these property methods are there. We have the property result. Now we have to go to the simulation environment. So we press simulation environment. It comes here. Now the first simulation, we have to add a heater. Okay, so go to exchanger. This heater, thermal and phase state changer, model heaters, coolers, condenser, etc. So let us use this heater. We have to give it a name. So let us name it heater. Press it here. And then it should have material input, feed, and this is the product. Now here we have to rename it, say hydrocarbon. We rename it, and then we press next. So this hydrocarbon inputs we have to give. So what is the temperature and pressure? It is 15 degrees centigrade and 10 bar. So it is 15 degrees centigrade and 10 bar pressure. And flow rate 100 kilomole per hour. So we write 100 kilomole per hour. Now you have the option to give in other units, but we have kilomole per hour unit over here with mole basis, so we are using this directly. We can give it in mass base or volume base also. Now composition, we can give individual mole flow, but we have it in the mole fraction, so we have to write mole fraction. Then methane 15%, ethane 15.5, so we write 0.15, 0.155. So as you keep on increasing, as you keep on typing, the total mole is coming, the total mole fraction is coming over here. Now it should reach 1, okay? So propane 0.75, N-butane 0.11. So it is 0.075, 0.11. Cyclohexane 0.12, benzene and toluene 0.2 and 0.19. Cyclohexane 0.12, 0.2 and 0.19. So the total is 1. So we are ready with the input. Go to next. It opens the heater input block. So here again, heater, there are 3 information available. That is 40 degrees centigrade, 10 bar pressure, or pressure drop to be 0. Now here temperature we give 40, but pressure, if you give 10 bar, then the pressure will be taken. If you give it 0 bar, it doesn't mean the pressure is 0 or vacuum. It means the pressure drop is 0. Okay? And if you give -1, that means the pressure drop is -1. Any negative or 0 will be regarded as pressure drop, while any positive value will be regarded as the absolute pressure. So the moment I give 10 bar, the specification is complete with a blue tick. Now we write next. Now all the required inputs are complete, so we can run the simulation now. So please run. It will run the simulation and it will give you the sequence of messages. Processing input specifications. So calculations begin, heater, simulation calculation completed with no warning, no error. It is quite understandable because our flow sheet didn't have any complication. We have a feed which is being heated in a heater. Now here we can see the result. Double click and you will find the material result. So the outlet will have the temperature of 40 degrees centigrade because heater is maintained at 40. This is the pressure. Now as because pressure has been increased, so there are certain vapor fraction and liquid fraction of the entire thing based on the particular pressure and temperature. At that pressure and temperature, some of the content will be in a liquid form. So that's what it means. Okay. Now we have to add a flash over here followed by a valve. So flash, we will use this. So 2 outlet flash. This is 2 outlet flash and this is 3 outlet flash. So we have 2 outlets, so we will use this flash 2. Followed by a valve. So valve is there in pressure changer. So we will keep the valve over here and come back to the material. Choose this one, this material. Reconnect the stream, destination, this one. Then this stream will be connected to this. This will come out here and this will come out like this. Now we have to specify, already 2 is specified as it is the heater output, but the flash and the valve we have to rename first. So this one is we write it as flash and we write it as valve. Now they are not defined because we have to give the operating conditions in the valve and the flash. So press next. Here the flash input, let us see, there are 3 inputs available. It is adiabatically, there is no temperature loss, heat duty is 0, pressure is 10 bar or 40 degrees centigrade. Now we have to choose any 2 of them because it is asking any 2 between temperature duty vapor fraction and here between pressure duty vapor fraction. So we shall choose these 2, that is Q is equal to 0 and 10 bar. So we will choose heater duty which is 0 and pressure is 10. Then it is blue ticked. Next it will ask for the valve condition. The valve will be operated at 2 bar, the pressure released at 2 bar. So we write as 2 bar, outlet pressure 2 bar. Then it is ticked. Then again run the simulation. We can run it. Again no error, no error, no error. No error, no warning. And we can see the composition of the leftover gas. These are the composition of the leftover gas. So we'll see 30 moles. 30 moles have come out. Okay. Rest of the things will go down. If you compare 4 with 5, you see 30.566, this is the leftover gas, and this is 69.433. Total will be 100 kilomole, isn't it? So 4 and 5 there, 4, this is 4 and this is 5. So this is 30, this is 69, and this is 100. So this was it is. Okay, total is 100. Now this is going to the column 1. Now here we will have a rigorous calculation of distillation. So for rigorous calculation, we will use a column with rad frac. It is for rigorous 2 or 3 phase fractionation in distillation column, single column. So we choose rad frac. And the top of the distillate will go to isentropic compressor. So we choose, again go to the pressure changer, bring this compressor over here and connect with the material streams. So reconnect, destination here. Then here there are 2 outlets, right? This is for vapor distillate and this is for liquid distillate. Now we have vapor distillate over here because vapor will be compressed and to form LPG. So we take vapor distillate, connect to this, and this will be our LPG. Okay, and this will be the bottom product, which will be essentially the mixture of C6 and C7 products, aromatics. So to make the thing a bit better, we can keep it here, okay, and bring it over here. It will look better. It doesn't matter with the calculation, but just for the ease of simulation, we keep it over here.